Hi, I'm Kirk Weiler, and today we're going to be looking at inflection points and the second derivative test. This is going to be our final lesson really formally on second derivatives. So far you've looked at concavity with a little bit of a concavity and inflection point primer. You've looked at taking the second derivative and using it to determine concavity and the location of tangent lines. But today we kind of finish it off by talking about inflection points and looking at an application of the second derivative that's really rather neat. Now, as we now know, we know that a graph will be concave down if its second derivative is less than 0, and it'll be concave up if its second derivative is greater than 0. The location on a smooth curve where that transition occurs is what's known as an inflection point. Now, the geometric way of thinking about an inflection point is it's really where a curve goes from concave up to concave down, or vice versa. So for instance, right? That is just a beautiful transition. Maybe we have an inflection point somewhere around there. Or maybe we have an inflection point somewhere around there. Right? Inflection points are actually a little bit tricky to spot. But the point is, geometrically, they're that sort of transition from being concave up to being concave down. Remember, in terms of slope, right? Concave up, slope is increasing. Concave down, slope is decreasing. So, let's take a look at exercise 1, where we look at the simplest type of function that has an inflection point, the classic cubic, y equals x cubed. Alright, it says prove that it's got an inflection point at x equals 0, and then we're going to sketch the graph to verify. Well, again, in order to prove that it's got an inflection point at x equals 0, we have to just make sure we know what the definition of the inflection point is, which is it's a location where the concavity changes, which means it's a place where the second derivative changes sign. Well, there's our first derivative, and of course that's simple enough. Let's take a look at our second derivative. I'm sure many of you will probably use y double prime because it's more convenient than that confusing d squared y dx squared. But we'll get 6x, right? Now, probably stands to reason that setting 6x equal to 0 and getting x equal to 0, right? That tells us that that's where the second derivative is equal to 0. That doesn't tell us we have an inflection point there. Yeah, you got it. It's time for our number line to show up again, right? Now it's a number line of the second derivative, not the first derivative, not y prime. Out of there, right? And the way that we really justify that we have an inflection point is we put down where our second derivative is equal to 0, and then we test points like, x equals -1. What do we test it in? We test it into the second derivative because that's what we're analyzing the sign of. So if I put -1 in there, clearly I get -6. Of course, that doesn't matter. What I just want is I want a negative, right? And if I put x equals +1 in there, into the second derivative, I get a positive. Now, it would be a little misleading to put those kind of arrows on here that we did before, because that typically indicates increasing and decreasing. And sure, we do have things that are increasing and decreasing here, specifically the slope. But it might make more sense to think of it in terms of sort of like a concave down portion of the function and a concave up portion of the function. But that's kind of up to you. I'm going to just erase this really quick so that we have some room. The final thing I'd like to do is just sketch the graph. I'm really hopeful that y equals x cubed is a power function whose graph you know. The thing about y equals x cubed is it looks a lot like y equals x squared when x is positive. One of the big differences, though, is it kind of looks like -x squared when it's negative. And notice that what we have there is an inflection point. Right? And it's an inflection point because clearly here it's concave down in this region, and here it's concave up. And of course that's exactly what the analysis here told us. Alright, but that's a very simple function with a very simple inflection point. Let's take a look at exercise 2. Way more complex. We've got a quartic now, and it wants us to find the x-coordinates of all inflection points, and key here, justify. I really want you to understand the justification on here. right? Inflection points by definition are where y double prime changes sign. That is the only way we can justify the existence of an inflection point. Y double prime changes sign. So quite clearly, if we want to figure out where y double prime changes sign, we need to have y double prime. So 4x cubed minus 12x to the first. And let's grab some y double prime now. 12x squared minus 12. Think for a moment. Pause the video if you need to. If we're trying to figure out where y double prime changes sign, then what should be our next step? Did you think of that? In order to figure out where y double prime changes sign, we're going to first figure out where y double prime is equal to 0. Right? For continuous functions, and this quadratic that we're working with here is a continuous function, right? We can only change sign if we pass through 0. That's the intermediate value theorem. Alright, pause the video for a moment and solve this equation. Okay, hopefully you were able to very quickly work out the fact that x squared must be 1 and x must be plus or minus 1. Now keep in mind, those two x values are not necessarily locations of inflection points. They're simply places where the second derivative is 0. Just like with local maxes and mins, right, we can have locations where the first derivative is equal to 0 and not have a turning point. Likewise, we can have locations where the second derivative is equal to 0 and not have an inflection point. But we'll get to that more in exercise 3. What we're going to do now is we're going to do something very similar to finding local maxes and mins. We're simply going to lay out a number line of y double prime. Put in a little -1, put in +1, and test values. What are we going to test values in? The second derivative. That's why it's a number line of the second derivative. So if I test x equals 0, I'm going to get a negative. Let's say I test x equals 2, I will in fact get a positive. If I test x equals -2, I'll also get a positive, telling me that the graph of y is concave up, concave down, concave up. So we should give some kind of conclusionary statement like IP's inflection points at x equals plus and minus 1 because y double prime changes sign. Alright. Now, of course, what's kind of neat is to take the graphing calculator and actually look at what this function looks like. If you haven't actually done it yet, please follow the instructions in the problem, graph this function on your calculator on the intervals that are given, and draw a little sketch. I'm just going to get the axes going. Why don't you pause the video for a moment and do that exercise? It's good for us to do things like this, right? Because it allows us to verify graphically and also understand better these graphical features. Right, here's a quartic, classic quartic, 3 turning points, etc., etc. Very easy to see where the maxes and mins are. Harder to see these inflection points, but good to be able to visualize them. And once you draw them in, you can kind of see, oh yeah, sure, we're concave down in here, right? Second derivative's negative. We're concave up in here and here. Right. Always try to verify your work on your calculator or other things when you have the opportunity. Let's take a look at exercise number 3. If I had to list one of the top 5 misconceptions in calculus, it would be that every time you have a second derivative equal to 0, you have an inflection point. We want to try to squash that out right now because it's just not the case. In exercise 3, it says, given that y equals x to the 4th plus 2x, show that even though the curve has a location where y double prime equals 0, it does not have any inflection points, and then we want to take a look at the graph again. Alright, pause the video and maybe think about this for up to 5 minutes. Try to find the second derivative, think about why it's got a place where y double prime is 0, but it doesn't actually have an inflection point there. Pause the video now and work on this problem. Okay, let's take a look at the analysis. Well, clearly the first thing that we have to do is actually find y double prime, so let's find y prime. That looks like a g. I apologize for that. So there's my y prime, which is 4x to the 3rd plus 2. And let's find y double prime, which is going to be 12x squared. Now it's clear that we can find a value of x for which 12x squared is 0. That means obviously x squared is 0 and x is equal to 0. So there's definitely a location where the second derivative is equal to 0. It's equal to 0 at x equals 0. The question is, why isn't that the location of an inflection point? Now, if you haven't figured this out yet, I want you to remember what the definition of an inflection point is. It's where the concavity changes, which means it's where the second derivative changes sign. So pause the video and again think about it if you haven't figured this out. Alright, let's talk about it. The reason that we don't have an inflection point there is because if we do a sign analysis on y double prime, right? Little sign analysis, put our 0 on, pick let's say x equals 1, substitute it into the second derivative, we have a graph that has positive concavity. The slope is increasing. Likewise, if we take x equals negative 1 and we substitute it in here, again we get a positive second derivative. So we have a graph that's concave up and a graph that's concave up. We don't have an inflection point, right? No IP because no change in sign. Now pause the video for a moment if you haven't graphed this thing yet, and take a look and see what this graph looks like. Do you have it? Alright, let's take a look. Again, it's always good for us to verify what graphs of functions look like when we've got some information about them. It's just beautifully drawn up there. This one is not the prettiest function on earth, a little quartic combined with a linear. But if I can draw it more or less the way it looks, kind of like this. And it's kind of interesting because there's definitely something going on around x equals 0. Almost looks like the function's fairly linear there. I wonder if there's some kind of connection on that. But regardless, there's no doubt that sort of everywhere along this curve, if we were to draw the tangent line in, the tangent line would lie below the curve. Remember, that's what we know about things that are concave up. The tangent line lies below them. Alright, let's move on to the second half of the lesson, and this truly is a completely different focus. The first half of the lesson focuses on inflection points. The second half of the lesson focuses on something called the second derivative test for relative extrema. Now, that is a mouthful, but here's what we're getting at. Normally, when we think about relative maximums and relative minimums, which you see there on your screen, normally we think about finding them with kind of a two-step process. We find all the locations where the first derivative is equal to 0, and then we analyze a sign, or we do a sign analysis of the first derivative to make sure that the sign of the first derivative is changing. I'm going to pause the video right now to clear up some technical issues. Alright, and we're back. Thanks. So, really, when we have a local maximum and a local minimum, it's all about the first derivative being equal to 0 and the first derivative changing sign. But the remarkable thing is that we can actually use the second derivative to figure out whether it's a local max or a local min. Take a look at these two pictures because I think they really get the job done. When we're looking at a situation where we have a relative maximum, there's really two things we know right at the location of the maximum. I don't know, let's call it x equals a. One thing that we know for certain, obviously, is that the first derivative, f prime of a, has got to be equal to 0. But the remarkable thing is that we also know at a relative maximum that we must be concave down. Seriously, try to draw a smooth relative maximum, that is. A smooth relative maximum where it's concave up. So what we also know is that the f double prime value must be less than 0. We can do the same sort of thing for a relative minimum. So we can say, well, the first derivative would have to be equal to 0. And since it's concave, oh jeez, concave up, that's concave down. Sorry about that. Here, since it's concave up, we know that the second derivative must be greater than 0. So we've got this amazing deal where we can actually figure out now whether a place where we have a horizontal tangent line, a place where the first derivative is equal to 0, whether it's a local max or a local min, not with a sign analysis, but with a single value of a second derivative. So let's take a look at exercise 4. It says find and classify all relative extreme values of this cubic function using the second derivative test. All relative extreme values, that means relative maxes and mins. Maxes and mins, right? So we got some cubic, it's the typical thing, right? And what we want to do is we want to find these guys. All right, so let's do it. I mean, one thing that we always have to know is we have to know where we've got first derivatives equal to 0. I mean, even if we're going to use what's known as the second derivative test, we still have to locate the horizontal tangent lines. That's pretty easy to do here. We end up having x equals plus or minus 1. Now, previously what we would have done at this step is we would have drawn out a first derivative number line, and we would have put on -1 and 1, etc. ... We're not actually going to do that this time. What we're going to do is we're just going to figure out whether the graph of the function is concave up or concave down at both of these x values. So for that, let's figure out y double prime. Y double prime is going to be just easy, right? 6x. So let's take a look at the line of logic. At x equals -1, y prime is equal to 0. And y double prime is equal to -6. So we've got a graph that clearly has a horizontal tangent there, but must be concave down because the second derivative is negative, right? Concave down. So therefore, we have a local max. And if we were pressed to explain why, we'd say because the first derivative is equal to 0 and because the second derivative is negative. So likewise, at x equals +1, we can say that the first derivative is equal to 0. The second derivative is equal to +6. So again, we've got some horizontal tangent, but the graph is concave up. So we must have, therefore, a local minimum. Isn't that kind of neat? So instead of doing this long drawn-out sign analysis to figure out whether the first derivative goes from positive to negative or negative to positive, we simply need to take our critical values, substitute them into our second derivative to determine whether it's positive or negative. How cool is that? Let's take a look at the last exercise. In number 5, it says that we've got a function, f. We don't know what its formula is, but we know it has a horizontal tangent line at x equals -3 and has a second derivative given by that kind of beastly looking expression. And then it asks, is x equals -3 the location of a relative minimum, a relative maximum, or neither? What I'd like you to do is pause the video and think about what we just talked about with concavity and see if you can come up with any conclusion about what type of feature x equals 3 represents. Pause the video now. Alright, so let's try to boil it down. Let's see what we know about x equals 3. We know that it has a horizontal tangent line there. So immediately, regardless of everything else going on, f prime of -3 must be equal to 0. So whatever it looks like, whatever the graph looks like, it's going to look something like this, or something like this, or something like this. Or, of course, it could look something like this. I ran out of horizontal line. Alright, well, regardless, we got to figure out which one is it. Is it a max, a min, or neither? Alright, well, what we can now do is, given the expression we have, f double prime of x equaling x times x plus 2 times x minus 4 quantity squared, we can determine the concavity of our curve at -3. So I'm going to evaluate f double prime of -3. That's going to give me -3. I do this addition in my head. -3 plus 2 is -1. And we have -7 squared. That's going to be +3 times 49. And you know what? I'm feeling a little bit lazy here. I don't really care what that is. The only thing I really care about is that it's greater than 0. That's all I really care about. For the record, it's 147. But I don't really care about that. I just care that it's greater than 0, because what that tells me is that the graph of f of x must be concave up. Right? It's gotta look like this. Which means because I have a horizontal tangent line there, and it's concave up, we must have a local maximum. Alright, that's it. Thanks for joining me for this lesson. Until next time, we will hope that you keep asking questions and that you keep doing math and that you keep ignoring my young daughter screaming in the background about taking her bath. Thank you, everyone. See you soon.